So what we're going to look at now in this video is we're going to be looking at how do we find the volume of a solid, but when the disk or washer method is prohibitively difficult. When basically the figure that we're looking at or the function that we're looking at is not really going to be amenable to, in fact, finding its volume when we revolve it around an axis using the disk or washer method. So let me give you an example. Let's say, for example, I have the equation y equals, and we'll do something like 3x squared minus 2x cubed plus 3. Okay? And what you'll notice here is that because this is kind of a polynomial, it would be really difficult if we wanted to say, for example, we want to revolve around the y-axis. Okay? If we want to revolve around the y-axis, what I need to do is I need to write x, right, as a function of y. But if we look at this equation, it's actually really difficult to write x as a function of y, right? I mean, you'd probably have to go in and do some kind of like completing a cube. The algebra here would just be really tough. And so consequently, we're not actually going to do that. What we're going to use is we're going to use a different method where we don't actually have to switch out the function. So let's look at this graph. Look at this graph, and what I've got here, I've got an intercept here at 3, okay? And I've got, it kind of looks something a little bit like that maybe. Something along those lines, down that way, or maybe the other way around. Doesn't really matter. What's going to matter is that now I'm going to try and revolve this around that y-axis. Okay, so we're going to be looking to revolve around the y-axis and construct some kind of solid of revolution around that y-axis. Okay, we'll go from this bottom line, we'll call it a y0, up to y1. Okay, right? And what we'd think about is we want to say, okay, well, how long is this thing here, right? Normally, if we were using that disk method, we'd say, well, what's that radius right there, okay? Well, let's kind of take a look at what would happen now if we kind of thought about this from a different way, if we thought about this from a different way to visualize. So let's say, for example, now I'm going to just take this piece right here, okay? And instead, what I want to do is I want to figure out, okay, I'm going to want to figure out basically the volume of this cylinder, okay, the volume of this cylinder. And what I'm going to try and do is I'm going to take really, really thin cylinders, all right, tiny little cylinders, okay, and I'm going to stack them up, just like I was stacking up before I was stacking up these discs. Okay, now with these cylinders, I'm going to stack up a bunch of little, very, very thin cylinders. Okay, very, very thin cylinders, and we're going to, kind of congeal them all together. So here's the concept that we're working with, right? So I've got this cylinder, all right? And if I look at this cylinder, I wanted to kind of figure out what its volume is. Basically what I would do is I would find, the overall, we take the circumference, okay, the area here, the area that's working here, and we then multiply it by that length or that height, okay, and then we multiply by the thickness, okay, and then what you can imagine, you kind of like stack them up. So like maybe like Russian babushka dolls, or the other one is I don't know if they still have these. They're beer cozies, right? So like it's this thing that you put your cup in, okay? Or you can even imagine this piece of tape. And this piece of this roll of tape. This roll of tape kind of makes some sense because what we're going to do is we're going to imagine that we've got really, really, really thin pieces. That we've got really, really thin pieces, and we're going to layer those pieces one on top of the other like this roll of tape, right? We're going to layer them, layer them, layer them, layer them, okay? Until what we get is we get like the entire figure. Okay, and those layers, each one of those layers is going to be slightly different depending upon what the function looks like. All right, so what's going to happen is we're going to get changes in this height, right? But the radius is going to be dependent upon how far away we are from the axis of revolution. All right, and I'm going to draw a picture of that to show you. So now let's look at how it is that we'll go about actually finding these volumes mathematically or analytically. Okay, so what we want to do is we want to imagine that if I've got a cylinder, okay, and basically, or like, as I said before, my string of tape, my beer cozy, okay, its volume is going to equal, right, basically, let me write it down here. Its volume is going to equal the surface area, like how much surface area that we have for the cylinder times how thick the cylinder actually is. Okay, so basically it's going to be surface area times thickness. And that's the cylinder. So if we think about the surface area for a cylinder, we've done this actually before, is going to be 2 pi r times h times, and then our thickness, whatever our thickness actually happens to be. Okay? So here's h, here's r, here's our radius. Okay? So it's going to end up being 2 pi r times our thickness. 2 pi r h, excuse me. Circumference, right? Okay? Times the height times the thickness. So now let's take this over to the graph, and we're now going to call these each VI, because what we're going to do is we're going to stack up our cylinders. So let's imagine that I've got some kind of delta x, right? I mean, we're doing integration, so you got to have delta x, right? And delta x is going to end up being our thickness. So delta x is the thickness. We're rotating around the y-axis, okay? So you can kind of see there's that. There's the y-axis. And like all the other kind of integration that we're going to do, we're going to, like this value here, that's some value of x. We're going to be changing with respect to x, okay? So this is going to end up being, that radius will equal x. And actually, or some value of x, and we're going to call this xi star. Okay, xi star. And so xi star is the midpoint of the interval. So it's going to be the middle point of the interval, and that way it gives us kind of like an average size for our thickness. It's going to give us a good estimate, right? A good estimate for vi star. All right, and so r, my radius, is going to equal xi star. Now the height now, if you now look, well, here's the height for that cylinder, the cylinder that we created. Okay, that cylinder that's got that thickness right there. So there's the height, and that's y, which is equal to f of x, or in this case, f of xi star. Excuse me, let me write that over here, f of xi star. That's going to end up being the height. So that's the thing that's going to be changing as the function changes. So x is going to change, okay, and then as x changes, as the radius changes, we're going to get a change in the height of our cylinder. Okay, so h equals f of xi star. Okay, and so consequently our vi will utilize just this, okay, is going to end up being 2 pi times xi star times f of xi star times delta x. And there we go. So our approximation for our volume is going to be an addition of lots and lots and lots of these. So like we might, we'll go over to the next interval. We'll find its next xi star, right? Okay. And then we'll evaluate what its thickness is right there for that cylinder, right? And we're going to do that all the way down from x naught to x1, okay? Or x naught to xn, excuse me. However long the interval actually is. Go to x naught to xn, and that's going to be how we're going to go add up all of these volumes, right? Just like we've done previously. We're going to accumulate all these volumes, all these little volumes, all right? Until what we have is we have the entirety of the figure, all right? For whatever that looks like. So my volume is going to be approximately equal to the sum I equals 1 up to n, I equals 1 up to n, of 2 pi times xi star times f of xi star delta x. So that's going to be an approximation, all right, for our volume. So if you think about it, oh, okay, cool, I get this, right? Look at that and think to yourself, all right, well, what's the next step? If we're actually doing integration, we want to think analytically. The next step is to actually take the limit as n goes to infinity of all of these to make each one of the thicknesses, right, decrease the thickness, increase the number of intervals. Okay? And as we do that, as we take limit as n goes to infinity, okay, what we're going to end up getting is we're going to end up getting the integral. Okay, so let's take a look at that. Okay, so what we've got now is we've got an approximation. We've got the volume is approximately equal to the sum, I equals 1 up to n, of each one of our VIs, right? Each one of those little volumes that are the shells, each one of those cylindrical shells. And that ends up equaling the sum, I equals 1 up to n, of 2 pi times xi star times f of xi star times delta x. Okay? Now, as we've been seeing inside of the section, what we're going to do is we're now going to take the limit as n approaches infinity. So we're going to make each one of those, we're going to make lots and lots and lots of intervals. Okay? And then we're going to take that, and it's going to be the sum, I equals 1 up to n, of now 2 pi, again, times xi star, times f of xi star, times the delta x. And what we know now is that what ends up happening, I mean, one, this is the definition of the derivative, but what's going to happen is that as those intervals get smaller and smaller, their midpoint becomes the actual value for x. So that midpoint is the value of x because, like, we now have, you know, infinitely thin intervals, so there's really only one point along that interval. So this ends up equaling the integral from x0 to x1, whatever our interval is, of 2 pi x times f of x dx. And that is the formula for the volume. So this is going to end up equaling the volume. That's V. So that's your formula for actually finding the volume using cylindrical shells when revolving around the y-axis. Now that's really important. And it's really important because if you notice when we do discs and washers, revolving around the y-axis with discs and washers, we actually have to transform all of our functions into functions of y, and we instead use y and we find the integral with respect to y. Okay? In this case, when we're revolving around the y-axis, you're going to be integrating with respect to x and utilizing the formula that goes along with x. So, what about if we're revolving around the x-axis? Well, if we're going to revolve around the x-axis, our volume is now going to equal the integral of, we're going to go from y0 to y1, 2 pi y times f of y dy. So now, when we revolve around the x-axis, what we're going to be doing is we're going to be integrating with respect to y, utilizing the function with respect to y, and having our interval with respect to y. Okay? So it's the exact opposite of what it is when we're using discs and washers. So let's take a look at an example now. All right, let's say, for example, I want to find the volume for the solid obtained by rotating the region bounded by y equals 0 and y equals 2x squared minus x cubed around the y-axis. So the first thing that I want to notice is that if I use discs and washers, then what I would need to do is I need to transform y equals 2x squared minus x cubed must be written as a function of y. And that's actually really hard. I mean, algebraically, I don't think we're going to be able to do that. So consequently, we're going to try, right? This can't be done. So we're going to try cylindrical shells, all right? And so that's our first step is to see, well, you know what? I think this is actually going to be better served by using cylindrical shells. So now I'm going to draw a picture of it in order to help give myself an idea of how it is, what this function looks like, and how I'm going to visualize my radiuses and my heights. Okay, so this is basically what the function looks like. It's got a y-intercept and an x-intercept at 0, 0. Okay, so there's 0, 0. And one of the other things I need to do is I need to figure out what this other value is here, because we're going to be rotating. Here is y equals 0. We want to actually rotate this region here around the y-axis. That's the region we want to figure out. So I need to figure out what this is, and this will be right that like my x1, y1. Okay, so I'm going to set y equal to 0. So 0 equals 2x squared minus x cubed. Okay, and so that's going to equal x squared times 2 minus x. And so that means that x equals 0 and x equals 2. So consequently, my integral, when I find my volume is going to equal the integral from 0 to 2, because since we're rotating, we're using cylinders, we're going to utilize our x values when we rotate around the y-axis, right? So when we're doing that horizontal rotation, okay? All right, so we go from 0 to 2. So this is 2 something. Y1 doesn't really matter at the moment. Okay, and now what I want to do is I want to utilize my picture to visualize what the values are going to be for my radius, okay, and for my function, or my radius and my height. Okay, so my thickness I know is going to be dx. That's my thickness, that's dx. And now my height, oh, there you go, there's the height, and that's the value for the function, right? This height, y, h, is going to equal 2x squared minus x, because that's how high it is. That's equal to y. So we've got that piece there. So I've got 2x squared, minus x cubed. 2x squared minus x cubed, right? And I've got dx. And now I need just my radius. Well, my radius, no problem, right? There's the 2 pi, is just going to be values of x, because we're just going to move along that x-axis, changing our height as we move along the x-axis, and just accumulating more and more and more of these really, really thin cylinders. So it'll be 2 pi x times 2x squared minus x cubed dx, right? We go through, we integrate to find our volume. And that's it. So what this is really about, and you'll get better and better at your integration as you work more and more with your integration, but what this is really about is it's about how do we visualize finding this volume? How do we determine that we're going to utilize cylindrical shells? And then once we do, how do we imagine what the height is and what the radius is going to be? So let's look at another example. Let's suppose we want to use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. So now what we want to notice is that we're going to be using cylindrical shells and we're going to be going about the y-axis. So since we're going about the y-axis, we want to integrate with respect to dy, with respect to y, okay? So I'm going to draw my picture, see what this looks like. And you should draw the picture every single time. In fact, I'm going to require it on your exams. All right, and here's 0 to 1. But what we're doing, okay, is we're actually going with respect to y, so it's going to be 0 to 1 on the y-axis. And it turns out that that's 1, 1 there anyways, and this is 0, 0, because we're using y equals the square root of x, okay? But it is important to remember that when we're looking at a region, all right, or we're discussing a region, that we've got to figure out which axis that we're actually rotating around and which ones we're going to integrate with respect to. All right, great. So now what I want to do is I want to imagine, what one of my cylinders is going to look like. So let's take this one right here, okay, and I'm going to draw my cylinder. Okay, I draw my cylinder. Doop. There you go. And there's my cylinder right there. And my volume is going to equal the integral. It'll go from 0 to 1, because that's my region, and it'll be 2 pi. Okay, and then what I want to get here is that there's my radius, right? There's my r, and r is just whatever value of y I have. So it's going to be 2 pi y, because r equals y. Now my height in this case is a little bit trickier. Okay, if we notice right here, that's the height that I'm looking for. That's h. All right, h. And one thing is that since I am going about the x-axis, I'm going to need to change square root of x into a function of y. So we go y equals root x. That's going to end up being equivalent to x equals y squared, which is great. So does that mean that h, okay, here's the question, does h equal y squared? And so we take a look at that for a second. Does h equal y squared? And the answer is no, it's not. Okay, it's not. This is y squared. That's y squared right there. or actually, excuse me, that value right there is y squared. Okay? So that length that we're looking at there, it's x equals y squared, right? And, or in fact, I should write that that's y squared down there. This length right up here, we've got to be a little bit more clever. It's going to be, we start at 1, and then we'll subtract out the y squared. So our h, in this case, is 1 minus y squared, right? We start at the top point, we subtract out the piece, right, that we don't want, and that leaves me with the rest of my h. So now I've got 1 minus y squared, and then dy. Okay? And then all you've got to do now is just go in and integrate. This one actually is a power rule integration. It's not too hard. Okay? So this is actually really important. You must absolutely, whenever you're doing volume, draw a picture of the region and then think about, and even maybe write down, I write all of them down, what is that height, right? What is that radius? And ensure that you understand what that height and that radius is as you are constructing your integral, right? And that's going to actually, in fact, cut down on your mistakes, okay? And once again, we've got 2 pi r times our height times our thickness. We integrate all of that and we end up with our volume. All right, now let's take a look at another example, but now what we've got is we've got 2 curves. So before, when we were working with discs and washers, we could deal with these 2 curves by imagining like cutting out a piece of the circular region, and that would basically allow us to find our volume. In this case, it's going to be a little bit different. Okay, we're going to have to do some different visualization. But first, let's draw a picture. Okay, and here's y equals 2x, and here's y equals x squared. Okay, there's y equals x squared. And what we want to do is we want to take this region here, and we're going to rotate that around the y-axis. All right, and so since we're rotating around the y-axis and we're using, we're going to use cylindrical shells. Remember, that means, okay, we want a function of x. We're going to integrate with respect to x, and our interval is going to be with respect to x. So what I'm going to do, what that's going to do then, is I'm going to imagine my volume. So my volume is going to equal the integral, and I'm going to need to find my interval here. So my interval, I'm going to start out, I've got x squared is going to equal 2x, right? We'll set the 2 functions equal to each other. And then that means that x squared minus 2x is going to equal 0. So x times x minus 2 equals 0. And so x equals 0 and 2. All right, and that actually ends up giving me my interval along the x-axis, okay, which is great, right? We're going to go from 0 to 2. So the volume 0 to 2, and it's going to be 2 pi. And since we're integrating with respect to x, it's going to be 2 pi x. And now what I need, now I'm going to need that height. That function right here is going to be the height. And the reason why I keep focusing on the height is because in different situations, in different scenarios, what we're going to get, you're going to have to think about how your functions work differently each and every time. Okay? And if you just concentrate on what does the cylinder look like and how do I calculate its height for each individual cylinder, then you get a much more versatile way of thinking about finding your volumes via cylindrical shells. So let's imagine that I've got this piece right here. Okay, got that piece right there. And so that's the cylinder that we're looking at. Okay? Now, we know that our value for our radius, that's the x value. Okay? That's x. We know our thickness is dx. And now I need to figure out how large is that piece right there. Okay? How big is that height? H. Well, if you think about it, we've been doing this now quite a lot when we wanted to find the area between curves. We also have been thinking about it a lot when we worked with our discs and washers, right? That's going to be 2x, all right, because that's the top curve, y equals 2x, and then it'll be minus x squared. So this value here is the 2x value, and here's the x squared value. We subtract the 2, or x squared value. We subtract the 2 of those, and that ends up giving me my height. And that's how you end up finding the volume. All right, that's the integral that we generated for the volume. Then you go in, you integrate, and you actually have the volume by the cylindrical shells. Okay. So again, what this should emphasize is it should emphasize the drawing and visualizing aspect of finding volumes by cylindrical shells. Okay, you're going to see a lot more examples here. You're going to have some questions about it, and as you do, make sure that you ask me either if we're in class together in class, if you need to on the discussion boards, or inside of our supplemental instruction. Okay. So that ends actually our lecture on volumes by cylindrical shells. The idea here is pretty much that we're going to take the surface area times the thickness of any one cylinder that we generate, and the trick here is always going to be one, to figure out what are you integrating with respect to, where are you revolving around, right? If you're revolving around the y-axis, you're going to integrate with respect to x. You're going to find functions of x. If you're integrating with respect to the x-axis, then you're going to do the opposite. You're going to use functions of y, and you're going to integrate with respect to y. Then the trick is to find what the value is for, we call it this our f of x or f of y, which is the height of each individual cylinder. All right, so this ends the lecture, and good luck.